Quantum physics tells us something astonishing. At the smallest scales of nature, particles don't always behave like ordinary objects. Sometimes, they seem to exist in several possibilities at once. Scientists use a special kind of information carrier called a qubit. Unlike a classical bit that stores only 0 or 1, a qubit can exist in a mixture of both states simultaneously. But qubits don't naturally stay in these mysterious states. Something has to place them there. In quantum computing, that role belongs to one of the most important operations ever invented, the Hadamard Gate. The Hadamard Gate performs something extraordinary. Starting with a qubit in the state 0, it transforms certainty into possibility, creating a perfectly balanced superposition. In many ways, it is the gate that teaches quantum computers how to dream in multiple realities at once. The computer checks them one by one. But a quantum computer has another strategy. A classical machine must test each possibility individually. If the answer hides behind door number 999, patience becomes expensive. The Hadamard Gate gives quantum computers a remarkable advantage. It allows a qubit to represent many possibilities at the same time. This ability is called quantum parallelism. The computer doesn't simply follow one path. It evolves through many possibilities simultaneously. It may look as if the computer explores many universes at once. Physicists still debate the interpretation, but mathematically, the effect is undeniably powerful. Grover's algorithm begins with Hadamard gates. They prepare every possible answer in superposition before quantum interference amplifies the correct one. Shor's algorithm also depends on Hadamard operations. Without them, finding hidden mathematical patterns would become nearly impossible. Even quantum teleportation begins with a Hadamard transformation, creating the conditions needed for entanglement and quantum communication. Inside modern quantum processors, Hadamard operations are executed with astonishing precision, often using carefully timed microwave pulses. Few quantum gates are used as frequently as the Hadamard gate. It is often the very first operation a quantum computer performs. That strange coin from the beginning was never magical. It was behaving exactly like a qubit transformed by a Hadamard gate. The Hadamard Gate teaches us perhaps the most profound lesson of quantum computing. Before a quantum computer can solve extraordinary problems, it must first learn to embrace uncertainty. The Hadamard Gate gives the qubit a very special push. Instead of flipping it completely, it moves it into a balanced state between 0 and 1. After passing through the Hadamard Gate, the qubit behaves as if it has an equal chance of being measured as 0 or 1. It now exists in superposition. Mathematically, the Hadamard Gate is surprisingly elegant. Its matrix contains only 4 numbers, yet those numbers create one of quantum computing's most important effects. Apply the Hadamard Gate to a qubit in state 0, and there becomes an equal combination of 0 and 1. Starting from 1 produces something even more interesting. The superposition now carries a hidden phase difference represented by a minus sign. That tiny minus sign changes everything. Quantum algorithms depend on interference, where waves either reinforce one another or disappear entirely. Imagine an orchestra playing the same notes, but one section changes its timing ever so slightly. Suddenly the entire melody sounds different. Quantum phases behave much the same way. The Hadamard Gate is far more than a mathematical trick. It is the doorway through which nearly every major quantum algorithm begins its journey. Coin that refused to choose between heads and tails. The Hadamard Gate taught us that quantum computers don't begin by searching for one answer. They begin by considering many possibilities at once. Instead of opening doors one after another, a quantum computer uses superposition to explore an enormous landscape of possibilities simultaneously. Quantum algorithms then use interference to suppress wrong answers and amplify the right ones, guiding the computation toward a useful result. That's why the Hadamard Gate appears almost everywhere in quantum computing. Before a quantum computer can solve extraordinary problems, it must first learn to embrace uncertainty. The Hadamard Gate doesn't calculate answers by itself. It does something perhaps even more remarkable. It gives quantum computers permission to imagine many answers at once. And sometimes, the path to discovery begins not with certainty, but with the courage to explore every possibility.